Our next speaker is Kevin Knott from Oxford Instruments, and he'll talk about flexible benchtop time domain NMR for R&D.
Thank you. So as I said, I'm Kevin Knott. I'm product manager for the time domain NMR systems at Oxford Instruments. And I'd like to thank the Ivan organizers for inviting me today to give my talk on benchtop time domain NMR. So I should start by mentioning that time domain NMR, and more broadly nuclear magnetic resonance, including benchtop NMR spectroscopy, are part of the Oxford Instruments materials analysis solutions, alongside atomic force microscopy, Raman, and detectors for electron microscopy for looking at chemistry, composition, structure, and in situ measurements. As was mentioned earlier today, time domain NMR is proven as an analytical QA/QC tool, and I hope to show some examples where the technique is used more broadly for materials analysis. So the purpose of my talk is to contrast the TD NMR against the NMR spectroscopy measurements, describe its application to a variety of materials, as well as giving some perspective of current and future uses in the polymer, food, pharma, battery, and construction industries. Firstly, I need to point out that the differences extend beyond acquisition of a spectrum or a time domain signal, as the hardware must be optimized for the particular measurements. And indeed, the magnetic field strength and homogeneity doesn't need to be as high as that required for spectroscopy, and this means that the measurements are less sensitive to the sample type, shape, and homogeneity, although we do need ppm homogeneity to prolong the free induction decay signal. Furthermore, the probe and receiver are optimized to minimize dead times between the RF pulse and the first valid data point. So this enables us to measure solid and solid light materials. So lower magnetic field strength and homogeneity means spectra cannot be resolved, and it also restricts the number of sensitive nuclei available for practical applications. But it does, however, allow increased sample size up to 53 millimeters, depending on the pole gap of the magnet being used. Another advantage of using TD-NMR is to measure a variety of samples, whether they be solid, liquid, powders, or paste. Also, typically, we don't need to change or destroy the sample. We can measure inside samples and processes non-invasively, or better still, measure samples inside the glass or plastic container without opening, even if it has an aluminium cap. So I often get asked, can we do these TD-NMR measurements on a spectroscopy instrument? Well, of course, it's possible to run the same pulse sequences. However, you can only measure liquid signal from a small, often unrepresentative sample. So, as you well know, the simplest example of the time domain NMR signal is the free induction decay, which consists of a variety of components that can be distinguished by their phase or state. There are no oscillations due to chemical shift differences because these cannot be resolved. And the signal from the solid and crystalline polymer components decay fast. Signal from solid-like components such as amorphous polymer, bound, or residual moisture has similar but slower decay. And in comparison, oils and fats have a long decay. So I'll start by describing the application of TD-NMR to measuring the physical properties and composition of polymers. So polymers are rigid, so it's often not possible to measure very short T2 relaxation using the CPMG experiment. However, we can measure free induction decay or solid echo for the T2 star relaxation. In this example, we used the solid echo to identify three components. So high in the gray, intermediate in light blue, and low cross-linking density in the dark blue. You can see that samples A, B, and C alongside here are distinguished by the proportion of these three components, which can be used to optimize or maintain their physical properties. An advantage of the relaxometry measurements is that they do not require calibration, although it is often preferred to have another physical, usually mechanical measurement to compare against. In addition to cross-linking density, there are a variety of other parameters which can be calibrated against NMR. And last year, an ASTM guide was published on the use of TDNMR for measuring polyolefin properties such as iron solubles or polyethylene density, thus further establishing it as a tool for quality assurance and control. Another very common use, and perhaps the earliest examples of TDNMR is in food science. We measure signals from water, fat, and sometimes side materials. However, it is the water relaxation in particular which is of interest, as it's sensitive to the local molecular environment. So one of the recurring themes of this presentation is the use of standard time domain NMR measurements to drive sustainability in a variety of industries. For example, the replacement of animal with plant-based products that have similar or better sensory or functional properties. So in this example, we are studying the texture and shelf life of cakes, which have been formulated with egg replacer. T2 relaxometry not only visualizes water and fat content, but also their environment, which relates to the mobility. Probably not unsurprisingly, the fat populations, which you can see here, remain fairly constant through storage. However, inevitably, the water T2 relaxation decreases as the cake stales over time. The same measurements can also be used to investigate heating and cooling processes in this and other food products. In contrast to relaxometry, water fat diffusion is another tool with which to determine microstructure in foods. So if we take a food emulsion, such as margarine, for example, there's a continuous oil phase, which contains water droplets here, also known as disperse phase, and the water molecules inside the droplets are limited by the droplet boundaries. As a consequence, water diffusion is restricted. Of course, diffusion is measured by using a pulse field gradient experiment and increasing the power and duration of the gradient pulses, or the time between them sensitizes the echo signal to the molecular diffusion. An emulsion contains both oil and water, which you would only want to measure one of. Therefore, T1 filtering is applied to remove the signal from the continuous oil phase in the case of margarine. The diffusion curve will consist of a composite of all the droplets in the sample. Therefore, software is required to separate this single curve into all the separate droplet sizes, which it is composed of. So the graph on the left here shows example data from the oil in water emulsion, such as like a food dressing, for example, but also a water in oil emulsion, such as margarine. So droplet size measurements commonly used for margarine, and it's particularly important for low fat spreads, which have higher water content because the droplets must be small, less than 10 microns, to avoid microbiological deterioration. As an aside, droplet size measurements can also be applied to non-food emulsions, such as paints, for example, allowing optimization of their stability and performance. And the graph on the left here shows the droplet size distributions in a variety of formulations with quite different compositions and therefore properties. So why would you use NMR? Well, traditionally, methods to measure droplet size are optically based, which makes it difficult to analyze opaque samples. Some emulsions, such as margarine, are unstable, so the temperature needs to be regulated. And in the case of margarine, at 5 degrees. Also, measurement and data analysis can take hours, particularly since the data is often analyzed manually by the operator. So in contrast, NMR measures the whole sample non-destructively. The emulsion can be stabilized at desired temperature, and both measurements and data analysis are fast. approximately 5 minutes, which means it can be used as a quality control in the foods and other industries. So pharmaceuticals is another area where TDNMR has particular advantages due to its ability to measure non-invasively and non-destructively. For example, it may be used as a fast, easy, and non-destructive replacement for Carl Fisher. So moisture measurement is important to prevent powder caking during manufacture, as well as to ascertain the stability of the finished product. So, for example, tablets or lyophilized proteins. And the advantage of the TDNMR is that you don't need to destroy the tablet or open the vial and expose it to air and moisture, which leads to inaccuracy. Furthermore, it's a bulk measurement, therefore sample uniformity is less of an issue. And as an example, Abraham and et al. Measured 16 milligrams or 5% water concentration in the lyophilized monoclonal antibody in 5 minutes. So TDNMR can also distinguish between amorphous and crystalline content of raw excipient materials and the resulting tablets. And this is important as the tablet structure will affect how the water penetrates, providing pathways for the drug release. It's also possible to measure a wide range of water contents in other samples. For example, we recently published a paper with Duaka Sangaraju and Kenji Kurita from Genentech, where we used time domain NMR to measure moisture in stool samples. So currently the moistness is assessed by the Bristol stool form scale. So hypothetically from less than 10% to over 90% water content. However, there is interest in a more objective measurement that could be used to correct for metabolites, protein, RNA, and DNA concentrations. So calibration was generated by drying one sample, then adding known amounts of water to produce the linear curve. All samples to be measured could be contained with another tube, so it is biosafe, and no sample preparation is required. Throughput is high as the measurement takes just a few minutes, and of course the same sample could be used for other bioanalyses. As well as diffusion and droplet size, which we mentioned earlier, we can also use magnetic field gradients for imaging. This is of great interest in measurement of sedimentation in injectable pharmaceutical suspensions contained within vials, syringes, or cartridges, since the uniformity will influence the dose precision. For a cylindrical sample, only a 1D gradient is required along the length of the tube or probe bore, which is under the influence of gravity. An example on the right here shows a model sample containing particulates in glycerol. The signal at the bottom of the tube decreases as the particle concentration increases, and conversely, the signal at the bottom of the tube, the top of the tube increases with the glycerol concentration. So Zhu and co. Monitored sedimentation of model samples in syringes, non-invasively, non-destructively, as they were stored at 2 different temperatures over a period of a few months. And then subsequently, they investigated respendability. Another emerging area where TDNMR has been recently applied is in batteries, and in particular the slurries which are used to make up the anode or cathode. When speaking to a range of manufacturers, we found that performance of cells can vary considerably, even if everything in the manufacturing process was seemingly constant. However, we found that time domain NMR is a very quick and obvious test for the variability in these slurry mixtures. So we have 2 examples here where the components in the mixture were the same. The cathode mixture consisted of lithium transition metal oxide, carbon black, and binder. And the anode mixture was just graphite and the binder. And the only difference between each of those was the mixing process. However, you can see a difference between the cathode mixtures. And it's very noticeable from the relaxation behavior of the slurries. The anode difference is more subtle, but still identifiable. In both cases, these measurements we completed in less than 10 minutes and could easily be run near a line on the neat product, so no sample preparation will be required to ensure consistency throughout the manufacturing process. Following on from that study, we looked at the mixing time and its effect on the relaxation behavior of the cathode material, and you can see clearly that the relaxation behavior, or in fact the relaxation times, increases with increased mixing time. So the investigation of concrete and cement is another mature field where TDNMR has been used. However, with many industries, to drive towards sustainability means it's necessary to do different. For example, slag, which is a byproduct of the steel industry, is typically used to make concrete. However, the drive to make sustainable steel also means this is no longer an option. Therefore, people are looking for other local materials which can be used instead. To that end, TDNMR can be used to investigate the setting characteristics of different formulations. Obviously, water is a large component of the mixture, and its mobility is an important property of investigating the setting behavior of concrete. So the graph on the left shows the T2 decays of mixture 1, and the corresponding T2 distribution is shown by the solid line on this graphs here. And the dashed line is from another mixture, mixture 2. It is evident that the mixture 2 has more strongly bound water from the get-go, and it hardens quicker as a result. And setting of mixture 1 shows more pronounced multi-component behavior, whereby the largest component is not necessarily the strongest bound. This is clearly shown in this kinetics graph for the proportion of the strongest bound fraction in each mixture. So we can see that mixture 2 here exceeds the bound water proportion of mixture 1 after only a few hours, and then far exceeds this over the next 20 hours. Obviously, this relates to just one aspect of the concrete performance. In addition to investigating different compositions and hardening, TDNMR can also be used to measure porosity and pore size distribution, as well as investigate freeze-thaw properties. Ultimately, TDNMR is a useful tool which can be used to develop sustainable cement and concrete, enabling the industry to meet its net zero targets. Now, a round-robin study was carried out and a report published by the University of Surrey and the UK National Physical Laboratory on the use of T2 reaximetry to characterize the pore size distribution in cement-based materials. As far as I'm aware, this was the first published study of its kind comparing the performance of various TDNMR instruments, which also gave recommendations on making consistent T2 measurements on these types of materials. So to conclude, I hope that I've given you an understanding of how a broad range of TDNR measurements can be applied to a variety of materials. And I hope you take something away from this presentation which might apply to your own interest. I thank you for listening, and I'm happy to take some questions now.
So any questions? Okay, thank you, Kevin.
Okay, thank you.
Okay.